Perfect. Okay, so as one of your friend asked during the break, the behavior of the root locus when S is too large is that. So in the previous lecture, we said that if a test point is included in the root locus, we said that K times N of S over D of S should satisfy certain angle conditions, okay? And that is the angle condition that needs to be satisfied. So the angle of that thing should be a multiple of 2 pi plus 1. But when S is too big number, okay, so if S is a complex number, when it has a very big real part and a very big imaginary part in the order of 10 to the power 6 or whatever, then these numbers 1, 2, 3, 4 do not matter, okay, so you can neglect them. So you can approximate the behavior of this K times N of S over D of S by the polynomial 1 over S cubed, or 1 over S to the power N minus M, and N minus M is the difference between the order of the denominator and the numerator. And that has to also satisfy the angle condition that we wrote in the very previous lecture. Therefore, as S goes to infinity, when S gets very large numbers, the root locus tend to follow these asymptotes, or they go to the one of the roots or one of the open loop zeros. I should also put some maybe arrows over there to indicate that. So this guy is going that direction. Okay, so it starts from the -1 point open loop poles, goes to open loop zeros. So these two guys are moving towards each other, meeting there, and then breaking away, and then they're following this trajectory. Okay, and this guy goes in that direction. Okay, something like that. All right, so let's continue with the intersection of the root locus with the imaginary axis. Okay. So how can I find the intersection of the root locus with the imaginary axis? So what I'm looking for is basically, I'm looking for the roots of the closed loop transfer function denominator. So I'm looking for d of s plus k times n of s equals to 0. So we need that space over there, n of s equals to 0. So how can I find the intersection of that equation with the imaginary axis, roots of that equation with the imaginary axis? So I simply can say that I can replace s with j omega because the root is going to be purely imaginary, and solve this equation, right? So when we have the j omega intersection, imaginary axis, I will have two roots s1 and 2 with plus minus j omega. Okay, I will have purely imaginary poles. Okay, imaginary roots in that sense. Okay. All right, so here I don't know omega and I don't know k, but I do have one equation. So how am I going to solve that? Any suggestions? So one thing important in this course and in this lecture is that we are working with equations of complex numbers, all right? So sometimes you will end up with a polynomial expression of a complex number being equal to 0, and you might think that I have only one equation and I can only find one variable. But the thing is that when we are talking about the complex equations, from every equation we get two sub-equations in the sense that I should have the imaginary part of that equation be equal to 0, and the real part of the left-hand side of that equation should be equal to 0. Okay, and from there I will have two equations, and I can solve for two unknowns. I can solve for k and omega. We will do that in our examples, by the way. Okay. And what is another way of finding the intersection with the j omega axis? Can you name something, a method? find the j omega intersection. A method that we have learned very recently is the Rath-Hurwitz method. Okay, so we can apply Rath-Hurwitz to ds plus k n of s equals to 0 and find the and inspect the j omega crossings there as well. Okay, because when we have imaginary roots over there, we can detect it by applying the Rath-Hurwitz method, right? Rath-Hurwitz. So there are two ways to find the intersection of the root locus with the imaginary axis. You either write down ds plus k n of s and replace s with j omega, or you again write d of s plus k of n of s is equal to 0 and apply Rath-Hurwitz. So whichever you're comfortable with, you can do that. And the last thing we mentioned in the previous lecture was the breakaway and break-in points. And the breakaway points are the points where two roots get together. Okay, so when we have the double roots in our root locus, and then they break apart, or sometimes in our other examples, sometimes the some poles are going to come from the complex plane and merge on the real line, and we will call these points as the break-in points. So this is a breakaway point because two poles come together and break apart and follow and starts to have the complex parts. So this is the breakaway point. Sometimes the reverse occurs and the two poles meet on the real line and follow the real lines. That's called the break-in points. So simply a breakaway or in point, break away or in point is a point on the root locus, is a point on the root locus where there are repeated roots, okay, where there are repeated roots. Like double roots, triple roots, okay? So basically what we're saying is that our closed poles become double roots, okay? So let's say P of S is equal to D of S plus K times N of S, okay? Is equal to 0. And if P of S has double roots, okay, has double roots at S is equal to S0, okay, then I can claim that P of S0 is equal to 0, okay, and the derivative of P prime of S0 is also equal to 0, okay. So that's how I will find the breakaway and break-in points by solving these two equations in the root locus. So let me write it down. So I do have D of S plus K times N of S is equal to 0 when S is equal to S0 when I have double roots, okay? And I do have D prime of S plus K times M prime of S is equal to 0 when S is equal to S0. And what I can do is that, so in order to find the K value and the corresponding roots over there, so I will just simply say that K is equal to minus D of S0 divided by N of S0. I get it from the first equation, and I can replace it in the second equation, right? So I will write down that D prime of S, and then minus D of S divided by N of S times M prime of S at S equals S0 is equal to 0. And I can write that thing as, in a one equation, I can summarize everything in one equation, saying that D prime of S, N of S minus d of s n prime of s is equal to 0. Okay, so solution of that equation gives me the break-in and breakaway points. Okay, to this equation gives the break away or in points. Okay. And when you find the roots, that you can find S0 by solving this equation. And how are you going to find the corresponding K value? By replacing the S0 in this equation, right? You can find the K value as minus D S0 divided by N S0. So the roots of this equation will give you S0, and the corresponding K value will be D of S0 divided by N of S0 times minus 1. Okay, so one important thing about this condition is that, so when you find the corresponding K value at the beginning of the root locus, we assume that K is a variable between 0 and infinity, a positive number. So you should check that in order to check the validity of the break-in or away points that you find by solving this equation. You need to check also that the corresponding K value is greater than 0. Okay, so simply this condition is necessary but not sufficient. Okay, so condition is necessary but not sufficient. Okay, so we have to check K greater 0 condition as well. So most of the time when we are trying to sketch root locus, you will find multiple solution to this equation. Okay, so there will be multiple roots satisfying this equation, but some of them will corresponding to negative K values, some of them will corresponding to positive K values. Okay, and you will eliminate those because you will find, we assumed at the beginning that the K is a positive real number. So you will eliminate the rest and use the ones with the K greater than 0 to find the breakaway point. And in this example, that is somewhere between -3 and -2. For some positive K value, those two poles move towards each other and coincide, and then they become a double root at this very specific point. And for that is called breakaway point, and we found it by using this equation, checking that the K is greater than 0. Okay, do you have any questions? So we will solve some examples, but...
Hocam eksi 3 ile eksi 2'den hangisi üst asimtotu istiyor acaba yol olarak?
I'm sorry, what? For the timing, it doesn't matter. Okay, so which of the rules are following the other, it doesn't matter. Okay. And remember that this is the approximate path that the root locus is following. So that details we are not interested in. Okay. All right, so let's solve another example. And I will add one more layer here and get rid of this one. And solve another, example. So in our next example, our open loop transfer function is equal to K over S cube plus 9S squared plus 11S minus 21. And this is equal to K over S plus 7 times S plus 3 times S minus 1. Okay. And this is given in the k times n of s divided by d of s form, right? And d of s. And what is n of s here? That is simply equal to 1, right? And I have no open loop zeros. I have only 3 open loop poles. And I'm trying to find the closed pole locations by sketching the root locus. Okay. So let's try to do that by first sketching the S-plane. Okay. Maybe I can do it a little further down here. And let me first place the pole locations on the S-plane. So one of my poles is at S is equal to 1. Okay, so this is, let's say 1. The other one is at -3. Okay, so this is, let's say, -3. And the other one is at -7. So let's say this is equal to -7. Okay, so maybe I will read more space there. So I will do that. Let's do this, something like this. Okay. So the first thing that I would like to say is that, so where does the root locus start? They start at the open loop poles and they end at the open loop zeros, right? So how many zeros do we have here? Open loop zeros. We don't have any, so the number of zeros is equal to 0. Let's say n is equal to 3 and m is equal to 0. Then all of the poles will go to infinity, right? As k goes to infinity. So, and they will simply follow the asymptotes. But before I find the asymptotes, I would like to first find the part of the real axis that is included in the root locus, okay? And for that thing, I will just check the test points on the real line. If I pick a test point over here as to the right hand side, I have no poles or zeros, therefore anything with greater than real part with greater than 1 is not included in the root locus. If I pick a test point between -3 and 1, I will have 1 pole, which is an odd number, therefore the section of the real line between -3 and 1 is included in the root locus. This part is included. But this part is not included because it has 2 poles to the right hand side, and this part is included because it has 3 poles to the right hand side of it. Okay. And the next thing I will try to find is the number of asymptotes. What is the number of asymptotes? So number of asymptotes is equal to n minus m, and that is equal to 3 minus 0, which is equal to 3. Okay. And what is the angle of the first asymptote? Angle of the first asymptote. It was equal to pi over n minus m, right? In absolute value. So it is equal to pi over 3. And what is the angle between the asymptotes? Angle between the asymptotes. It was equal to 2 pi over 3, right? So 2 pi divided by absolute value of m minus m, it was equal to 3. Okay. So once again, I will have asymptotes. The first one will be pi over 3. The other one is going to be pi. And the last one is going to be minus pi over 3. Okay. But I need to find the intersection point of the asymptotes, so place it on my root locus. And what is the intersection point of the asymptotes on the real axis? That was equal to summation of poles minus summation of zeros divided by number of poles minus the number of open loop zeros, okay? And that will be in our example simply equal to -7 minus 3 plus 1. That was the summation of poles. And the summation of zeros is equal to 0 because I don't have any 0. Divided by n minus m. So it's equal to 3 minus 0 is equal to 2. And that makes minus 9 divided by 3 is simply equal to minus 3. That is perfect because now I know that the intersection of asymptotes are over here. Okay. And the asymptotes will look something like this. The other one will be something like that. And the third one will be something like that. And it is kind of obvious that this pole at minus 7 will follow the asymptote with an angle pi, right? This will follow this asymptote. And the next question is this. So these two poles will move towards each other, right? So the pole at 1 and the pole at minus 3 will move towards each other. And they will meet somewhere in the middle, and then they will break away and start to follow the asymptotes. Okay. But for the timing, we don't know. It can happen here, for example. Okay. So that for all values of k, the system becomes unstable because there's always a pole on the right top plane. Or in another scenario, they meet somewhere over there, right? And then follow the asymptotes. Okay. Then I can conclude that for some small values of k, the system is still stable because all closed poles will remain in the left up plane, but after a certain value, the system will again be unstable. And how can I find that? Where they will meet? By finding out the breakaway or in points. Okay, so I write down as break away and in points. And I simply said that the equation that will give me the breakaway endpoints was d prime of s n of s minus n prime of s times d of s equals to 0. Okay. And n of s is equal to 1, so I can write it down there. So this is equal to 1. Then n prime of s is also equal to 0. So I will have a fairly simple equation such that d prime of s is equal to 3 s squared, here is d of s, plus 18s plus 11. Okay. And since m prime of s is equal to 0, the remaining part will be equal to 0, and that will be equal to 0. Okay, so solution to this equation will give me the candidates for the break-in or break-away points. Okay, and the solution to this second-order polynomial, the roots of the second-order polynomial is given as, I will write it down directly. S1 is equal to minus 5.3, okay, and S2 is equal to minus 0.69. Okay. So both of 2 points are candidates for breakaway or break-in points. Okay. And how should I check if they are on the root locus or not? I should find the corresponding k value, right? We said that k is equal to minus d of s divided by n of s, and I should evaluate that s is equal to s1 and s is equal to s2 and find the corresponding k values, right? And if you do so, the corresponding k value is approximately minus 25 for the first root and plus 25 for the second root. Okay, so which one of these points is a valid breakaway point? So the second one, right? We assume that k is a positive number at the very beginning of our derivation. So a negative k cannot be a solution for us. So I will reject the first root over here. And I will accept the second one over there where we have a positive k value. I have a double root, a breakaway point at the point when S2 is equal to minus 0.69. Okay, so, and also you can see that also here. So the thing is that, for example, the first candidate was minus 5.3 to somewhere over here, right? So, and since this part of the real axis is not included on the root locus, I can directly see that there is no positive k value such that I will have the breakaway point there, okay? Because this section of the root locus is not, so if of the real line is not included of the root in the root locus. But how about the minus 0.7? It is somewhere over here, right? So let's say this is the minus 0.69 points. And as you see, this section of the real axis is included in the root locus. So for some positive k values, my poles will pass through that point. And at that point, they will become double roots of the equation of the denominator of my closed transfer function. And then they will break away there and start following the asymptotes, okay? Something like that. It will be symmetric, so don't mind my drawing abilities, but those two lines should be symmetric to each other, okay? So they will go there. And that pole is going to follow the asymptote that goes to infinity, minus infinity, okay? So far, so good. So what is the remaining task? So we found the breakaway point, okay? We found the k value corresponding to, so between k is between 0 and 25, these two poles move towards each other and they meet at point minus 0.69, okay? And what is the next critical k value that I'm interested in? The k value where we pass where the poles pass from open left half plane to open right half plane, then the system becomes unstable, right? So let's find the intersection with the j omega axis as our next task. So we try to write it down. So let's say intersection with j omega axis, okay? And what I will do is that I will write first d of s plus k n of s equals 0, which is the denominator of our closed transfer function. I'm trying to find the closed poles by finding roots of this equation. And I will simply, I have two options. I will either simply change s with j omega, or the other second way is to apply the Rath-Hurwitz to this equation to find the j omega crossing. Okay, so let's write the denominator of the closed transfer function ds plus k times n of s. So d of s was this guy over here, so it is equal to s cubed plus 9s squared plus 11s minus 21 plus k times n of s, and n of s was simply equal to 1 itself. So this is p of s plus k of n of s equals 0 equation over here. And I will replace s with j omega there, okay? So let's say let s be equal to j omega. Then I will have minus j omega cube, okay, minus 9 omega square plus 11 j omega plus k minus 21 equals to 0. And once again, I said that, so we have one equation with two unknowns, with omega and k that I need to find. But the good news is that I have two equations here because I need to equate the real part to 0 the left-hand side and right-hand side, and the imaginary part of this equation to 0. Okay. So what is the real part of this equation? It is equal to, I will get this guy and that guy over here. It is equal to minus 9 omega square plus k minus 21 should be equal to 0. Okay. And from there, I can say that k is equal to 9 omega square plus 21. That's our first equation. So let's have a look at the imaginary part. I have minus omega cube plus 11 omega is equal to 0. Okay. So from there, I can simply write omega times 11 minus omega square equals to 0. Okay. And I do have now the solution to that omega is either omega is equal to 0. Okay, so I do have here either omega equals to 0 or omega is equal to, let's say, plus minus square root of 11, right? And the corresponding roots are s1 and 2 is equal to plus minus j times square root of 11. And how about corresponding k values? So if omega is equal to square root of 11, what is the k value over here? So omega squared is 11, so 99 plus 21. So it's like 9 times 11 plus 21. It's equal to 99 plus 21. That is equal to 120. Okay, so let me write down the corresponding k values over here. So for these locations, k is equal to 120. Another solution was omega was equal to 0. So when omega is equal to 0, what is the k value? So in that part, the k is equal to 21 simply. Okay. And that kind of makes sense in the sense that, so if we go back to our original root locus, we found that these j omega locations are actually, they are j square root of 11, okay, and minus j square root of 11, okay. And we also find the corresponding k values for that. So let me try to write that in another color, let's say green color, okay. Okay, so we said that when k is equal to 0, we have the poles, close the poles at +1 and -3. And when we increase k further, they pass, they meet somewhere over here. It was minus 0.69 or something. And they break away and they will follow the asymptotes over here. And we said that one of the omega was equal to 0, that k value was equal to 21. Okay, one of the intersection with the imaginary axis happens when j omega is equal to 0. And for the k value, this is the k value, sorry, k equals 21. So when k is equal to 21, this pole passes to the left half plane, okay? And when does the breakaway happens? So we found that k is equal to 25. The breakaway happens. So this point corresponds to the case when k is equal to 25. And if I increase k further, so somewhere over here, k is equal to 120. K is equal to 120. We have our second j omega intersection, okay, with the imaginary axis. And these two poles crosses the imaginary axis and passes to the right half plane over there. Okay. So again, this is also k is equal to, corresponds to the point when k is equal to 120. Do you have any questions? So we were able to identify all the critical points on our root locus. So intersection with the J-omega axis and the corresponding K values as well. So let me ask you one thing. So what is the best range of K to operate for this system, for the closed-loop systems, to be stable? So for K values between, so for K values between 21 and 120, all closed poles are on the left half plane. Okay. And when K is less than 21, there is one pole here which is on the open right half plane. Therefore, the system is unstable. When K is 21, this pole is passing to the left half plane. And then it means that K is 25 with the other pole coming from -3. And until I can increase K until 120, those two poles will move towards the imaginary axis. But if I increase K any further than 120, the system will become unstable because the closed poles will go to the right half plane. Is that clear?
Hocam 21 de dahil değil mi stability'ye? K eşittir 21.
No, not really, because in the previous lecture we said that if you have a pole at the origin, then you have a term at like 1 over S, right? And that's the integrator. So that's not a stable system. So for the system to be stable, all of the poles in the open left half plane, the imaginary axis is not included there. All right?
Tamam.
So, or you cannot have poles at the origin, then you cannot have a stable system. Okay. I mean the closed poles. And what is the other way of finding the J-omega axis crossings? So we will like to find the intersection with the J-omega axis. And what is the second way of doing that?
Root-Hurwitz.
Exactly.
Uygulama.
So we can apply the Roth-Hurwitz method. Okay. So let me write it like apply Roth-Hurwitz to d of s plus k n of s equals 0. Okay. And since we don't have time, I have to stop here. But you will see once again, if you do that, apply Roth-Hurwitz to this polynomial over here, once again, you will see that between k values 21 and 120, system is unstable. For so system is stable. For the values of k values larger than 120, system is unstable. For k values less than 21, system is unstable.